Let's talk about the Gauss quadrature idea. This idea, for me, it's a brilliant idea. Being a mathematician, this is really a wonderful idea. If it really works in practical situations, that's another topic that we will talk about in the next video and a little bit in the end of this video. But from the mathematical point of view, this is a brilliant idea, and it's only a little step from the Newton codes idea. So let's talk about this idea. I bet we will never know if I win or not. I bet that what we will do here was what Gauss did, and then he had his idea. And we don't want to apply the Newton codes formula. Instead of the natural choice, the first point is the left point from the integration interval, the last point is the right point of the integration interval, and the point in between is exactly in between of these points. Let's move this point a little to the right, and then let's see what happens. What did we see? There will be a matrix which is these values to the power of 0, to the power of 1, and to the power of 2 in the first column. Then we get that matrix 0 to the 0th power is a 1 in this case, to the first power 0, and to the second power 0. Then this point to the power of 0, to the power of 1, and to the power of 2. But we want to do it with these numbers, so to the power of 0 is 1, to the first power 2 divided by 3, and to the second power 4 divided by 9. Then the 1 is a 1, 1, and a 1. And then times the unknown weights, and then the integral values of the monomials, and these are always 1, a half, and a third. This is our problem, and now let's solve that problem. I want to do that by hand here. It's not so complicated. So let's take the second line and subtract the third line. So we have 2/3 times omega 1 minus 4 divided by 9 times omega 1. So 2 divided by 3 is the same as 6 divided by 9. 6 divided by 9 minus 4 divided by 9 is a 2 divided by 9 times omega 1. This cancels, that's why we did. And then on the right hand side we get this minus that. Half an hour minus a third of an hour is 30 minutes minus 20 minutes, which is 10 minutes, which is 1 divided by 6. And then let's multiply with 9 divided by 2, and then we get omega is 9 divided by 2 times 1 divided by 6, and then a 3, so we get 3 divided by 4. Omega 1 is 3 divided by 4. Then in the second equation we get 2/3 times our omega 1, 3/4, plus omega 2 is a half. What is that? Cancels. This is a half. A half plus omega 2 is a half. That means omega 2 is 0. And that's the spectacular thing in this calculation. So in 1 we have omega 0 plus omega 1 plus omega 2 is 1, and thus omega 0 is a quarter. So our solution is this vector of weights, and this 0 is spectacular. Why is that spectacular? Because if we apply this formula, then we get 0 times the value at position 1. And 0 times something is 0. So we do not really need to evaluate at position 1. That's the spectacular thing here. Let's say we do integration interval 2 to 5, f of x dx. Then what we will do, what is the formula telling us, multiply with the length of the interval, and then take these weights and multiply. Here it's, so these 3 points, this is 0, 1, 2 divided by 3, and now we have to map that to the interval 2, 5, and so 2/3 of that way, then that's the 4. So f of position 2 plus second weight 3 divided by 4 times f at position 4 plus 0 times f at the position 5. And so we have that. We don't have to evaluate at position 5. And that means this formula is exact for polynomials of degree 2 or less. And so we can be exact with only 2 evaluation points. When we did Newton codes with 2 evaluation points, we got the trapezoidal rule, which is only exact for polynomials of degree 1. But here, with 2 function evaluations, we are exact even for polynomials of degree 2. Okay, this is the spectacular thing. And I think this was the observation of Gauss. And then he said, okay, what if we choose not 0 and 2/3, but maybe 2 better points than these? Then maybe we can be exact even for polynomials of order 3 or 4. I think that was his idea. Okay, and then we can revisit our Newton codes equations, and then we can have a very, very good idea. And what is that idea? First, I want to do some recap. If we have a set of m equations and n unknowns, so maybe m is larger than n, or m is equal to n, or m is less than n, what do we know about a set of equations if this number does not match? Okay, first, what do we know if this number matches? For a linear system which is quadratic, this means that normally there's exactly one solution. Let's have an example. Maybe you have the following system: 2 equations, 2 unknowns, and a linear system. And so normally we will have exactly one solution. And if you try to solve it, you will easily find that solution. It's the solution in this case 2, 1, x1, 2, and x2, 1 gives a 5 and gives a 1 here. So this is the solution. And that's the normal case if you have a quadratic system. Okay? And if we have a nonlinear system, what is for a nonlinear system? There's normally not one solution, but a finite number of solutions. So maybe 1, maybe 2, maybe 3, maybe 0. Okay, that is also possible, but a finite set. Let's have an example for a non-linear system. Maybe x1 times x2 is 100, and x1 plus 2x2 is 45. This is a non-linear system. This equation is a linear one, but this one is a non-linear one. So in total, it's a non-linear system. And if you do here the calculation, maybe x1 is 45 minus 2x2, and then take that here, and then you get a quadratic equation. You can solve with the ABC formula, and then you will get this solution. 5 times 20 is 100, and 5 plus 40 is 45. But there's a second solution, and this second solution in this case is 40 and 2.5. 40 times 2.5 is 100, and 40 plus 5 is 45. That's the recap for m is equal to n. If we have more equations than unknowns, then normally we have no solution for linear systems and also for nonlinear systems. and the other way around, we have less equations than unknowns. Then for a linear system, we have infinite many solutions, and the same for nonlinear system. But to be honest, we are only interested in that case. If m is n, then there are normally solutions, but it's not guaranteed. And so now the idea from Gauss is, what was this system looking like? We formulated in the matrix formulation, but now I want to formulate without the matrix notation, but it's only the notation which differs. The content is exactly the same. And what were the unknowns and what were the knowns? That's the point of the great idea, so we have to make that really clear. The unknowns here are omega 0, omega 1, omega 2, but not x0, x1, and x2. So we formulated these three equations and not a fourth, a fifth, and a sixth one, because we expected that with three equations there will be a solution, and with 4 or 5 or even 6 equations there will be no solution. So these equations cannot be satisfied, most likely. And thus the formula, if we apply it, and so this formula will be exact for polynomials only up to degree 2. If you remember everything what I said, then you know this formula will also be exact for polynomials of degree 3, but this is kind of surprise. Normally the expectation is it's only exact for polynomials of degree 3. And now the great idea. If we see the x0, x1, and x2 also as an unknown, here we learned that with a clever choice of x1 we can get better formulas. Then okay, let's say x1 shall be what it ever will be, x0 and x2 also. So if we see them as unknowns also, then if we see the x positions also as unknowns, then the hope is we will get formulas which are exact up to degree 5. Okay, so let's do so. Here we have 6 equations and 6 unknowns, and then we can try to find the solution. But unfortunately, this time this formula is no longer linear. No longer linear. Only this equation is a linear one and all the others are non-linear, and then the theory for finding the solution is not easy. Really not easy. We will talk about that in the next chapter. If we have a system of equations and this system is non-linear, then it's really hard. Sometimes it's close to impossible to find the solutions. Okay, let's do so and let's check how far we come. But we will succeed, or one can succeed. Okay, let's have a look in my script. Okay, so we are in the chapter Gaussian quadrature. This is our idea. And then we get these 6 equations which are nonlinear ones. And now we try to find the solution, but we will not really try to do that, but I tell you what the solution is. We have 6 equations and 6 unknowns, and now we have to find the solution, or we have to find out if there is a solution. If you're interested in the theory, then Google Legendre polynomials, and then it will take a long time to understand every detail, and I don't want to do that. And the answer is here. x0, x1, and x2, and these weights then all 6 equations hold. You can check if that is really true, but I tell you, yes, this is really true. Okay, I see the numbering is different from the Newton-Cotes formula. Okay, in this chapter I number with 3. I hope that is not confusing. I think it's not really a problem. Okay, so with these positions and these weights we have it. But what is the situation if that is 0, 1 interval? Then these 3 positions are, it's the midpoint, and then it looks like that. So, but instead of doing like we did in that script in the mathematical theory, it's more common to see that as the standard interval, minus 1, 1, and then construct the formulas, and then you will get this. So here we have minus 1, 1, and 1 point is the 0, and 1 point is that one, and this one is that one. This is the square root of 3 divided by 5, so square root of 0.6 and minus that value, and then also square root of 0.6 with a plus. Okay, these are the 3 positions, these are the 3 weights, and then using these formulas you will have to do that. So this is the adjustment of these 3 values to your integration interval AB, and then you will use the midpoint, which is A plus B halved. A plus B halved is the midpoint, and then these 2 points, and B minus A halved is that distance, and then okay, we map that to that. And then we evaluate the function f at these 3 positions, and then we take these weights, these ones, and then we scale with b minus a divided by 2. This time we have a 2 because the length of the standard interval is a 2. And so this will be the formula, and this formula will be exact for all polynomials up to degree 5, and this is the stunning point. Okay, so in the next video we will do an example or 2 examples, but in this video we will not do so. But there's one remark. There's one point, and that means if we have a long integration interval, let's say this is the integration interval AB, then maybe we split this integration interval into maybe 4 parts, and then we apply on each part the Gauss formulas. And that will mean that we will evaluate at that point, at that point, and at that point for that part, and we evaluate for that point, for that point, and for that point. And now these distances are no more the same. So let's say if this is 0 and this is 4, this is 1, this is 2, and this is 3, then this distance is 0.77 and this distance is 0.48. This distance is 0.77 and this distance is 0.46, and so on. So if we don't have a function which we can evaluate wherever we want, if we are not in that situation, but we are in the situation that we have a table of values at given positions, maybe coming from measurements, then we cannot apply Gaussian quadrature. And so this idea only works for functions which we can evaluate wherever we want. Okay, so this was the first video about Gaussian quadrature, and in the next video we will see examples how to apply.